In this video, we would like to discuss a very geometric problem of finding an enclosed area. And at first, it's not going to be apparent in any way how this is related to calculus and what it is we're going to be talking about, but we will see how becomes a definite integral in a few minutes, and then on future videos we're going to make the connection between this definite integral, i.e. some type of enclosed area, and the idea of an antiderivative. So what we would like to do is find the area enclosed between a curve and the x-axis, between A and B. So we see in this picture kind of a nice enclosed area that we would like to calculate. Now, the problem is that it's not a familiar geometric shape. That is to say, it's not a rectangle, a circular type object, a triangle, a trapezoid. We have no common formula we can apply. So instead, we're going to take a slightly different approach. What we're going to do is try to approximate the area enclosed under the curve. And once we've approximated the area enclosed underneath the curve, we are going to try to make that approximation exact. So the first thing we are going to do is take the interval that we have and break it up into subintervals. So we're going to break this interval from A to B into n equally spaced subintervals. And if we break it up into n equally spaced subintervals, we will know exactly what the width of each subinterval will be. We will denote that width by delta x, and to determine it, you take the length of the interval, b minus a, and divide it by n, the number of subintervals you would like to have. So what we're going to do is let a be x naught, then we're going to break it up. So x1, x2, x3, and we're going to go all the way over here to, we'll have xn minus 1, and b is equal to x sub n. And just from a kind of formula perspective, I want to make an observation. So notice that if I want to know what is a way to think about x sub 1, I can think of x sub 1 as starting at A and going the length of one subinterval, so delta sub x. I can think of x sub 2 as starting at A, and we have to move two subintervals. So A plus the length of two subintervals. So that'd be A plus 2 delta x. Likewise, x sub 3 is A plus 3 delta x, and in general, the x sub I is A plus I delta x, something that will be useful in future problems. So now that we've taken this interval and we've broken it up, what should we do next? Well, the idea is to approximate the enclosed area on each of these subintervals and then add up those approximations. So the big thing we need to do is approximate the enclosed area above each subrectangle. Excuse me, above each subinterval. And let's go to another picture. So at this point, we've taken the interval from A to B, we've broken it up into n equally spaced subintervals, and on each of these subintervals, we want to somehow approximate that enclosed area. And the easiest way to do so, as drawn here, is to use rectangles, because that's a familiar geometric object whose area we can easily calculate. So on this first subinterval, we somehow have to determine what the height of that rectangle will be. And to determine the height of that rectangle, I've just looked at the right-hand endpoint, the x1, and I've gone up to the function there and I've used that as the height of the rectangle. So in terms of the first rectangle that we have, we can note that the height of this rectangle, I'll just say h, is f of x1, and the length of its base is delta x, because delta x was the length of each of these subintervals. For the second rectangle, similar idea. Its height we just determined at the right-hand endpoint. That is to say, I start at the x2 and I go up to the curve. then that's the height of my rectangle. So its height would be the function value, f of x2, and its base is delta x, and so on. So what we would like to do to approximate the total enclosed area is we will calculate the area of each one of these subrectangles, and then we will add them all up. And adding up all those areas is precisely where the sigma notation becomes involved. And we can very clearly see that this is not going to give us the exact area, at least not initially, because we have all of this extra area we're calculating above the curve. So it might be a bit too much. But let's see what this gives us. The area enclosed, so I'll say approximately, is equal to the area of the first rectangle. So the area of the first rectangle is f of x1 times delta x, where f of x1 is a height, delta x is its base, plus the area of the second rectangle, f of x2, its height, times its base, plus, and we keep doing this all the way until we get over to this nth in the last rectangle. For that last rectangle, its height is f of xn, and its base is delta x. So we go all the way up to f of xn delta x. So the area is approximately equal to, if we put this in sigma notation, we're summing things up from 1 to n of the form f of x sub I delta x. And a very, very important observation here is that what we are adding up here, the f of x sub I delta x, that quantity really just represents the area enclosed by the ith, what we might think of as subrectangle. So the question becomes, how do we get an exact value for the area then? Because all we have at this point is an approximation. And the key observation is the more rectangles you use, that is, the larger the value of n, the better your approximation is going to become. And you think, what's the most rectangles we can use? Well, think of the biggest possible number. Well, to get that, we need to take a limit, this concept we've discussed earlier this semester. The limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I delta x. And this is going to correspond to the exact area enclosed. And let's be very clear here to note the corresponding formulas as we discussed. Delta x is b minus a over n, and x sub I, which we can think of as being the right-hand endpoint of the ith subinterval, is given by a plus I delta x. So let's go ahead and connect this idea to something that we are going to call the definite integral. So I realize there's a lot of words here. So don't get too concerned with all of these words. All I want to do is really kind of note that this thing that we calculated on the previous slide, which ends up being an enclosed area if your function is positive, is what we're going to define to be the definite integral. So if we have a function which is bounded, just like we did, we take that interval from a to b, we divide it into n subintervals of equal width. So you have the x0, x1, all the way through xn, which are the endpoints of those subintervals. And then the only difference here is that when we calculated the height of our ith rectangle, we just plugged in the right-hand endpoint. You don't have to use the right-hand endpoint. In general, you can use these, what you would call a sample point, where x1 star is any point you want in the first interval. x2 star is any point you want in the second interval, and so on. And putting that together, we get the formula for the definite integral. Now, my tendency is to not worry about a sample point, but just to worry about using the right-hand endpoint. And the reason I like to maybe keep it in terms of using that right-hand endpoint is because it's something we can easily write a formula for. It's a plus I delta x. So that is what I think is the best way to go about it. So let's note the geometric interpretation. So kind of just summarizing what we had on the previous slide, going back to this key formula I want us to think about, is that the observation is the definite integral represents what I will call a net difference of enclosed areas. And let me illustrate this with two pictures. So if we consider a function, much like the one that we saw, on the previous slides, where it's a nice positive function from a to b. Then in this case, if you looked at whatever this enclosed area would be, we would say that the definite integral from a to b of this function f of x is equal to that enclosed area. But not all functions are entirely positive. So it's very reasonable that we would have maybe something that looks like this for our function. So going from a to b. And here you have this area enclosed above the x-axis. It's called that a1. And an area enclosed underneath, call it a2. So in this example, the definite integral from a to b of the function, we have this very nice geometric interpretation. It's the area enclosed by the function above the x-axis, a1, and we subtract away the area enclosed underneath the x-axis, so a2. So we have this very, very nice geometric interpretation that a definite integral represents a net difference of enclosed areas. So area above the x-axis minus the area enclosed below. In the next video, we will explore this geometric interpretation. Then in the following videos, we will explore going back to this definition and using this sum, which has a special name. This is something called a Riemann sum, and we will use that to evaluate exactly several definite integrals.